In this video, we're going to look at simple harmonic motion situations that contain more than one spring. Sometimes a mass spring system oscillating in simple harmonic motion may contain more than one spring. The springs might be in series, parallel, or even some sort of combination. In such cases, we need to find the equivalent spring constant. And if you're familiar with finding equivalent resistance or capacitance in a circuit, this concept is much the same. To find the equivalent spring constant, we need to know whether the springs are in series or parallel. Two or more springs are in series when they are connected end to end. So we can see in this example that the two springs are connected together, so we say that these springs are in series. Two or more springs are in parallel when they are connected side by side. But then what if I had springs that were like this? And I always find that students get stuck. So I made up my own definitions of series and parallel springs. So let's pretend that you're an ant and you need to crawl to the wall. So if you have to crawl through both springs to get to the wall, then the springs are in series. But if you're an ant on the mass and you want to crawl to the wall, and if you have a choice, the springs are in parallel. So you could crawl through this spring to get to the wall, or you could crawl through this spring to get to the wall. So these two springs are in parallel. So now let me apply my new definition to the third situation. So you're an ant on the mass and you want to get to the wall. So you could go this way to the wall, or you could go this way to the wall, which means you have a choice. So we now know that this third example is in parallel. A mass spring system with more than one spring functions as if it has only one K value, and the single K value is called the equivalent spring constant. The variable for equivalent spring constant is K with a subscript EQ. If you've already covered circuits, the equations to find KEQ are analogous to finding equivalent capacitance in a circuit, which is going to be opposite of finding equivalent resistance. So if your springs are in series, to find KEQ, it's 1 over KEQ equals 1 over the first spring constant plus 1 over the second spring constant plus 1 over any remaining springs you have in series. If they're in parallel, we just add up the individual K values, and that is going to give us the KEQ that we're going to take forward. So let's look at a quick example. Let's start with this system up here that has two springs in series. So here we have a looser spring that's got a K value of 50 and a tighter spring that has a K value of 100. So because they're in series, I'm going to use the 1 over KEQ equation. So I have 1 over KEQ equals 1 over 100 plus 1 over 50. And if I'm doing this, I'll say by hand, I'm going to start by finding a common denominator. So I'm going to leave my 1 over 100, and I'm going to rewrite 1 over 50 as 2 over 100. So now I'm going to end up with 3 over 100. But that's not the answer. That's 1 over the answer. So I have to take the inverse of that. So instead of 3 over 100, I'm going to end up with 100 over 3. So the K value is 33.33 newtons per meter. And so now if I had other questions that I was answering or other equations that I was using, I'm going to use the K value of 33.33 to function as the spring constant of this system. All right, the next example looks at two springs that are in parallel. In this case, both of the springs have the same K value, and the equivalent spring constant is going to be the sum of them. So I'm just going to add them together, and I have a KEQ of 200 newtons per meter. Let's look at a couple of examples. In example 1, a 5 kilogram mass is placed on two springs that are connected end to end. The top spring has a K value of 500 newtons per meter and the bottom spring has a K value of 200 newtons per meter. Letter A says calculate the elongation of each spring when the mass is attached. So in this situation, I can look at the springs individually if I wanted. So for example, if I look at the top spring, I know that when I attach that hanging mass, that hanging weight is going to create the restoring force in the spring. So therefore, mg is going to be set equal to Hooke's law, kx. So I add the 5 kilograms times 9.8. The spring constant of the top spring is 500. And we can calculate that the top spring is going to stretch 0.098 meters. Now let's do the same thing for the bottom spring. So the bottom spring has a different K value, 200. So it's a looser spring, so we would expect it to stretch more. And when we calculate it, we get 0.245 meters. All right, letter B says determine the equivalent spring constant. So these springs are connected end to end, which means they are in series. So we're going to use the spring constant equation, or the equivalent spring constant equation for springs in series. I can do 1 over 500 plus 1 over 200 equals, in my calculator, then 1 divided by the answer to flip it over, and I get a KEQ of 142.86 newtons per meter. Letter C says determine the total stretch of the spring combination. I can find the total stretch literally by adding these two numbers together, because I know how much the top spring stretches and I know how much the bottom spring stretches. But I also want to show you that you can use the KEQ to kind of do the same thing. So I could say to myself, well, I'm going to be adding a 5 kilogram mass, and that hanging weight is going to elongate the combination. And if I'm looking at the combination, then I'm just going to put in the K value of the spring combination, which is the 142.86, and I find out that the whole combination is going to stretch 0.343 meters, which is the sum of these two numbers. And then lastly, letter D says once it's set into oscillation, calculate the period of motion. So I can also use any of the other equations that we have for simple harmonic motion, and for the K value, when I have a combination, I just make sure that I plug in the KEQ value. So if we want to know what the period is, 2 pi square root of m over k, we're adding a mass of 5. We put the KEQ in of 142.86, and we find out that this spring combination will oscillate with a period of 1.18 seconds. In example 2, 3 springs, each with a spring constant of 300 newtons per meter, are attached as shown. A 4 kilogram mass hangs from the bottom spring. The combination is then stretched 20 centimeters and released, causing it to oscillate in simple harmonic motion. Letter A says determine the equivalent spring constant of the combination. So this one's a little bit more complex because I have 2 springs here that are in parallel, and then this parallel combination will end up being in series with the bottom spring. So let's start with the top 2. I know they are in parallel because if I was an ant on the mass and I wanted to crawl to the wall, I could go path 1 or I could go path 2, which means these 2 springs have to be in parallel. So let's start by finding the equivalent spring constant of those top 2 springs. So since they are in parallel, I just add them together. Now I have a spring constant of 600 on the top, and that 600 is going to be in series with this 300. So I'm going to use the in series equation, which is 1 over 600 plus 1 over 300 equals 1 over the answer to flip it over, and we find out that the entire combination together has an equivalent spring constant of 200 newtons per meter. And now I can take that K value and put it into any simple harmonic motion equation that we've talked about in the past. So here's just 2 quick examples. What is the maximum potential energy of this spring combination as it's oscillating back and forth? Well, the maximum potential energy depends on how far it got stretched. And we stretched it 20 centimeters, which is 0.2 meters. And I'm using the equivalent K value of 200. And we find out that we have a maximum potential energy of 4 joules. At that end point, that potential energy is also equal to the total energy of the system. So when I get to letter C, it says, what is the velocity of the mass when it is 0.1 meters from equilibrium? So it doesn't matter that it's a spring combination. I can still look at this in terms of conservation of energy. And I know that I have a total energy of 4 joules. I know now that my potential energy is not going to be at a maximum because I'm not at 0.2, I'm only at 0.1 away from equilibrium. I still used the equivalent spring constant of 200, and so I found the potential energy here, and then I'm going to add the kinetic energy, 1/2 mv squared, and I'm solving for that velocity. And we find out that the velocity when I'm halfway between equilibrium and the endpoint is 1.22 meters per second.